Okay, so today we're going to start off with mechanical dispersion. So this is mixing. Of the solutes due to variation in flow velocity. So mixing due to variations in flow velocities relative to the average velocity calculated by Darcy's law. So, the average flow velocity is from Darcy's law. But what we're trying to say is that mechanical dispersion is going to cause variations in that flow. So you're going to get some contaminants getting there before the rest by the average flow and some coming after it. And so, and this happens at different levels. So at the microscopic level, you can get, velocity distribution, within a pore due to friction. So, if you have a grain here and a grain here, you're going to actually get, so say you have two grains, you're going to get, you're going to get faster velocity down the center here than on the sides here due to friction as that water molecule is going through between two sand grains. So you're going to get this microscopic things, you're going to have this variation in velocity occurring. You can also get it B, variation due to tortuosity, if I can say the word, tortuosity of the flow path. So say you have a grain here and 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 here. So you can get some of the water going like this, some of it going this way, some of it almost going straight through and going through real fast, some of it going to be going around and going like this. And so since the flow paths change, so will the thing. So you're going to get more tortuosity, you're going to get slower movement, so the more that it has to move there and stuff like that. And then C, C down here, variations in pore size. So with this one is, say you have your grains here, and you have Gregor throat here, and then you have, so over here you've got this, and over here you have this. So you're going to have these larger ones going to be moving through faster, and then these smaller ones moving through slower. So, this flow path here. So variations in pore size can also cause mechanical dispersion on the microscopic scale. Next. So influences of macropore on dispersion. So let's see, influences of macroscopic factors on dispersion. Okay, so primarily due to spatial, so this is primarily due to spatial variations in the in conductivity and hydraulic conductivity. So heterogeneities. So, heterogeneities inside of your system. Heterogeneities, so if you have a homogeneous system, this won't cause it. But if you have heterogeneities, you'll have it doing this. So diffusion is also contributes to dispersion. So the other part of this is that diffusion also contributes to dispersion. Okay. So, like here in this area around here, we have sand lenses, clay lenses. They'll go back and forth. We can have a lot of variation just in a layered system. So, an example here. So we'll do an example. Would be something that would be a continuously. Let's look at a continuously layered system. Okay. So these are, so say you have a system where you've got layers in here. Okay. And each one of these has a specific conductivity. Where, say, like this layer here has the highest. Okay. And let's say this one down here has the lowest. Okay. And all of them vary somewhere in between them. Well, in the system with the highest K, you're going to get your contaminant moving further along than, say, in the slowest one. And then everything else will be somewhere else in there. And so in a layered system, you can get the contaminants coming through the different layers at different speeds. And so we can have this dispersion happening. And then say if we had our well crossing all these layers instead of being just screened in the specific layer. If it was screened across all of these, you would think, oh, it's really moving this fastest over here, when in actuality you could have a layered